Yep, I think we're all good.
Okay, and you're seeing the presentation there?
Yep.
All right, so thank you very much for that introduction, Ryan. And I guess you did all the introducing. So I'm just going to say that I'm going to present some work that has been done by my colleagues and myself with the Coastal Processes Group and the Center for Climate Change Impacts and Adaptation. So that's with Scripps Institution of Oceanography. And today we're going to talk about wave run-up, forecasting, and some cool new observations with a drone LiDAR. And the video that you're looking at here in the background is waves overtopping the riprap here. That's this pile of rocks that's at Imperial Beach. This is Cortez Avenue. So we're going to be looking at a lot of information on this particular site in the next few slides, and really trying to understand how to predict when something like this is going to happen, and what you need to know in order to get to that state. So just to give you a little bit of a background as to where we are. I am coming out of San Diego right here, and Imperial Beach is pretty much on the border between California and Mexico. It's the most southern city in California. And so I'll be presenting results at Imperial Beach, and also some drone results from Torrey Pines State Beach, which is just a little bit further north. And so both of these beaches are west-facing beaches. They are exposed to large swell events that are coming from the Pacific, both the north and the south. But in general, you do get these big run-up events when you do get these large storms offshore that are very far offshore. So these swell events. So as has been presented previously in this group, the total shoreline water level, I'm going to call it the TWL here, it's a combination of sea level rise, climatic and seasonal cycles, tides, oceanic eddies, storm surge, and waves. And it's the wave portion that I'm really going to focus on today. So Serafin et al. In 2017 estimated that on US West Coast beaches, run-up and set-up contributed more than 50% to extreme total water levels. And so understanding what these waves are doing and what the run-up actually is a really important part to getting a run-up forecast correct. And so I will just be focusing on this portion of the equation here. And so just to get all the graphics straight, today, and I know that you guys have seen this before too, but here we go. So the still water level is sort of the bathtub level surface. So that's including these long scale processes. And then you have wave setup and wave set down, and wave setup being the super elevation of those still water level at the shoreline as the waves are pushing all that water up onto the beach. And then you have the run-up excursion that's going as the swash goes up and down the beach. It's this vertical motion here that creates the swash. So we have wave setup and swash, both of those create extreme wave run-up. And so we're trying to forecast what happens or how high basically the waves are going to get up the beach. So by 2100, San Diego flooding days are expected to occur almost daily. This is from the NOAA intermediate sea level rise scenario. And what that means is that nuisance flooding that might be experienced now is more likely to occur, especially if it's happening almost daily, and it's more likely to damage our coastal infrastructure. So some examples of what that might look like for us in California is here in this picture, we have the Highway 101, which is a big north-south corridor where we're from, and the waves are encroaching onto this highway. And then you have the cliff top or beachside railroad, which is at times the tracks have been threatened by cliff failures, and so it's important to understand what the run-up is doing in these regions as well. And then these two pictures are from Imperial Beach. And so this looks like your average nuisance coastal flooding. It's a sunny day, blue sky, kind of large swell event flooding on the streets, but Imperial Beach also does experience some pollution coming from the Tijuana River estuary that's coming from the south there, and also a little bit further south at the at Punta Bandera. So things are heading into, I don't want to say they're heading into the streets, but pollution can also be an issue when you do have these coastal flooding events. And to combat this kind of problem at Imperial Beach, in the past, they've done extreme nourishments in front of these particular condos that we're looking at here. And this was from 2012, and there was a really large nourishment. And if you are interested in looking at this, Bonnie Luca has done a lot of work on tracking where the sand has gone with our group's observations that we get quarterly. And so the idea for all of this is that we need to have accurate early flood warnings, not only so that the city can plan for this kind of stuff, but so that you can get a baseline observations for coming up with any sort of adaptation strategy in the future. And so what we were tasked with at Imperial Beach was coming up with this forecast system. And here's an example of what it looks like. And this is for one particular street in Imperial Beach. And you can head to this website if you want to see that, plus the other locations that we're looking at. And really having this idea where you have a 6-day sort of forecast out into the future, your city planners can understand whether they are going to need to go ahead and bring in, you know, bulldozers to get the sand off the street, or even make some berms or something to combat the expected overtopping. And so in addition to this, we've also had sort of long scale observations of what the sand is doing. And again, definitely check out Bonnie's work if you are interested in what happens with the nourishment and at an erosional hotspot. So the forecast system here is a 6-day forecast of total water levels. And this has been developed to determine how uncertainties propagate through the estimate of total water level. So there's a lot of moving parts to this puzzle. On the development side, we have long-running observations to make our model. And we have wave observations from the CDIP wave buoy network just offshore that heads into the CDIP MOP forecast. And then we also have our surf zone bathymetry data from what our group has collected with jet skis and ATVs and push dollies on the beach. And so this kind of information is fed into a phase resolving model SWASH, which you have also heard about in this seminar. And because the phase resolving models are computationally expensive, we developed an emulator that's based off the extremes. So we're looking for eroded beaches and large offshore waves, and that is where you would expect to get the wave run-up itself. So that is the IPA, which I will be discussing a little bit further. This is the integrated power law approximation. So that takes into account the shape of the wave energy spectrum rather than just the bulk parameters. And the modeling study that created this IPA was validated with observations from a storm event itself. So operationally, we use this with a beach slope model that has been developed based on the latest observations that we have from LiDAR. And then we also are using MOP nowcasts, which are ultimately derived from WaveWatch 3. And then the tide and the non-tidal residual are coming from the La Jolla tide gauge, which is a little bit further north from Imperial Beach, but we found there to be not that much of a difference between the tide and the residual both. And so each of these components does have uncertainty. And so what we're trying to figure out is what the limiting factors are for getting these skillful predictions. What can you leave off? What can you, what do you really need to get correct in order to get the run-up right? And what spatial resolution do you actually need to have if you're going to be predicting wave run-up on a street scale like this, where we were just looking at one little street in Imperial Beach. So for this talk, I'm going to be focusing on the development side of things. So the creation of this IPA model that led into making this flood forecast. And then we're going to be looking at new observational tools that we're trying to use to make these forecasts a little bit better. And so that's enhanced observations with mobile platforms. And we'll get into that a little bit later. So without further ado, let's go into the IPA portion of the talk. And so this is all really created with the SWASH model itself. And so the SWASH model, this is a, get this started. It's a phase resolving model. It has been field tested, and it's been found to be accurate for both the surf zone statistics as well as the bulk runup. But in order to get that accuracy, you do need to get the offshore boundary condition correct and also the beach profile correct. So you need not only to know what the foreshore is, but you need to know what is under the water. And you also need to validate this with observations. So this is from January in 2019. And this is a nice movie that Cassandra Henderson has made in our group. And this is looking at LiDAR observations in the blue versus the SWASH model in the orange. And this is just going through in time, but then this is the wave run up here, like following this little line as it goes back up and forth. So you can see that if you are putting in the correct boundary conditions, that is, for this particular case, we did have a pressure and current meter offshore. And so, and it was a fairly longshore uniform kind of day, that you can get a very accurate estimation of what the wave runup will be if you're just using this model. So that's great. We think that the model works quite well for this area. Let's see. Ooh, graphics. Okay, so going into this model, the things that we're plugging into it to actually make it and separate from the validation portion of whether the model works is to plug in historical data so that we can simulate a bunch of storm events. And so this is information that's coming out of the CDIP wave buoy network and the Mont Pinecast. So the CDIP wave buoy network here creates this this model that we have at the MOP lines here. So every little red line here is we're calling it a MOP line. And these they extend to about 10 meters or 15 meters depth, depending on where you are. And at each of these locations, you can get a bunch of wave information. So that includes like the wave spectra and whether you're looking at radiation stress or anything like that. So everything is produced by the model out here at these little red dots. And then for the bathymetry portion, all the information that we're using here is from our historical stuff. So nothing with the LiDAR, but this is all collected with the ATV and the push dolly and the jet ski. And so in the past, these have been, quarterly surveys, and we have about 10 years in this particular location. And so what we can do with this is create a climatology of the storm events. So we're looking at cases where the waves are greater than 2 meters. That's what we're calling a storm for this particular spot. And we can also take the times when we would expect to see large wave run-up based on this. I'm calling it the wave run-up forcing. So this is offshore wave height and wave length, the square root of that. So if this is, or not the square root of that, don't know, messed up there. Anyway, big waves, that's what we're looking at. And the goal out of all of this is just trying to get the storm information. And then on the right-hand side here, we're looking at the historical bathymetry of this location. Sorry, it's a little bit fuzzy, but this is observations of profiles going back to 2008 in this one spot. And you can see that there are actually some extra things extending out here. That's when the beach was nourished. So we didn't include any of that information. We only wanted to go for the eroded stuff when you would expect to see large wave run-up. And so we plug those into the SWASH model itself. And then we're using 2 different offshore boundary conditions. So one of them is using a bound wave in the offshore, and the other one is assuming that there's no infragravity energy. So just different ways of treating the infragravity energy in the offshore to make sure that we are encompassing everything that could be in terms of potential errors there. And then on the foreshore, we're doing 2 different beach slopes. And this has since been expanded by a PhD student in our group, Atina Lange. So look forward to that coming up soon. And we also are looking at things at mean high water. So just above this line right here is where we're looking at, just because we want to find the conditions that do, again, make this wave run up happen, or large wave run up happen. So out of all these runs, we can go ahead and extract the 10 centimeter run up line statistics, and then we come up with the IPA itself. And the IPA is the integrated power law approximation. So the whole idea with this is that we're trying to use spectral wave information instead of just the bulk parameters. And so in a traditional run-up formula, such as the Stockton formula, which is very commonly used on sandy beaches, it's a combination of 3 different parameters. So you have the beach slope, you have the offshore wave height, and you have the offshore wave length. And you smush them together, and you end up with a model for what the wave run-up is going to be. And so sometimes that can create some issues, because you could have 2 very different spectra that are getting the same bulk answers. And so what we wanted to do was accommodate a broad and multi-peak spectra with a frequency weighted interval. So we're taking this information, but we are allowing the powers in here to vary in order to accurately convey all the information that is contained inside the spectra itself. So we're letting M and N scoot around when we're looking for best fit parameters for each of the components. So we're looking for setup, infragravity, swash, and sea swell swash together. So how well does this work? So if we're looking at the total run-up, or the R2%, and we compare a tuned version of the Stockton formula, keep in mind that we did have to tune it. If you don't tune it, then you are very off base for this particular beach. And if you compare that with the observed run-up in the model, you can get quite a bit of scatter. And that's not bad per se. This is about 1/2 meter root mean square error. So if you know nothing, it's not a very awful guess. You're pretty darn close. But if you use the integrated approach, but you're keeping the same sort of form, which is H0 L0 here, you can greatly reduce that scatter. So just by including all the information that is in the spectrum itself, you can make a much tighter fit. And so that is very promising. But then you can go even further and allow those powers to vary in a very not quite unit making sense kind of way, but it seems to work. And so there is a component out here that takes care of the units for you. So this is the integrated approach using the best fit parameters. And again, this error is greatly reduced from about 1/2 a meter to 1/5 of a meter. So this is good news. And so the big question is, does this work? We have the IPA, we created it, not using any data. This is prior to doing any sort of validation. And we're going to test this against actual observations from an event here. Let me get that going. So this is from January of 2019. And we had the forecast up and going at that time, but we were using the Stockton formula for this. And so we did expect there was going to be a large event. And so we got a LiDAR down here. So this is a terrestrial LiDAR that's mounted on the edge of this balcony. And we also had, at the same time, some instruments that were out there. We had a pressure sensor, 2 pressure sensors. We had a current meter, pressure and current meter offshore. And so the idea was that we wanted to observe this event to see if the forecast system was working. And so in terms of comparing it with the observations, We're looking at a number of different lines here, so I'll walk you through this. The observations are in the black dots for swash and setup, and then the combined are 2%. And the observed foreshore slope is in the solid blue line with the IPA, and then a modeled foreshore slope is in this orange line or yellow. And then using a Stockton formula, this is the dotted blue line here. And so when you're just looking at comparing with the observations and you're looking at SWASH itself, the SWASH is predicted well enough by all models, which is great. That's very good news. But the setup does have considerable error to it. And that lends itself to making the total run-up almost a meter off at times, just using the basic formula that is commonly used in these wave forecast models. And so the moral of the story here is that if you have the information, if you're able to incorporate as much as you can possibly incorporate, then you should go with having more data and trying the more complicated stuff, because hopefully you can reduce your error. And so we do have ongoing validation for this. This is from January of 2020, where we had the same sort of setup. We were also hoping to get another storm event. And I don't think it was that stormy, but the validation for this is ongoing because COVID. And here we are, and that's where I'm going to leave the rest of this talk. So we are still on the validation end side of things. We also have observations with occasionally pressure sensors that we have out at each of these points, and then people taking pictures and stuff to look at when things were flooded and when they weren't. And so that's the first part of this talk, getting the improved run-up forecast models and understanding where the errors are. And what we're trying to do is extend this strategy at Imperial Beach to other places in California. So we're trying to head to the California state parks and beaches, not only to do these high water level warnings at these locations, but also it's mainly to get these observations of the beach itself and getting these sort of baselines so that we can contextualize what the future change will be. And then once you can get that, you can come up with more cost-effective ways of getting an adaptation strategy for your particular location. And so this is done by our amazing field team in our group, and they have gone out during COVID. They've come up with ways to socially distance themselves and continue to monitor the beach. We now use truck LiDAR and then photogrammetry stuff, and now we have this new drone LiDAR, which is what I'm going to talk to you about for the next half of this talk. So here we are, new observational tools. And I'm going to talk to you about an experiment that we did at Torrey Pines that compared the drone LiDAR to a truck LiDAR. So let's talk about drones and LiDARs. Drones are cool. LiDAR is also very cool. And the thing about a drone LiDAR is that you can rapidly deploy it in a remote location and survey everything. So it takes about 30 minutes to set it up in the field, and you can use it for extreme event response. You can't necessarily have it out there during an actual extreme event. It's just a very expensive doorstop at that point. But you can also take it to remote locations. And one of the things that I like about this is that a lot of the observations that are made currently with LiDARs for understanding wave runup and looking at bathymetry is that you have this permanent tower or this large structure that you have to take somewhere. And you know, if we could build towers everywhere, we would. We want to understand how it is at all the different points of the beach, but we can't. So using the drone LiDAR is a great way of making sure that we can still get that information. And with the drone LiDAR, you can use it in the mobile mode where you're same as you would with photogrammetry. You're just moving along the beach, getting your scans with your LiDAR so you can get the whole alongshore picture of what things are, but then you can also hover over the surf zone and get wave scans. And so that's what I'm going to tell you about next. So we're looking at these line scans of a hovering LiDAR. And in essence, this is like just moving the tower to wherever you are based on the conditions. And so at Torrey Pines State Beach, what we did was we had an array of pressure sensors out here on the beach, and we had our DJI hexacopter here with a Regal mini bucks attached to it. And then we had our usual beach scanning truck. So this is the Regal VZ2000. And so these are two different wavelength LiDARs, and it was interesting to compare both of them together. But I'll show you what that looks like as we're scrolling along on the beach. So the red here is the drone, and the blue is the truck. And you can really see that from the truck itself, which was parked over here at the top of these rocks in sort of a stationary mode so that it was mimicking a LiDAR. There was a lot of shadowing. The truck could not see what was beyond these rocks just because of the low look angle. And it also couldn't see on the other side of the waves. So you can see the back of the waves with the drone, which is really great because you're able to, if you wanted to, you could probably fuse these two different observation methods to get a complete look at what the entire surf zone is doing. And so I'm going to compare two different deployments. We had one in December, one in February of last year, I guess it was now. And one had big waves with a pretty long period, and the other one had small waves with the same period. Both were at high tide. And we just wanted to see how well it did so that we could establish whether we could move it from this point and look at places on the beach that aren't necessarily as controlled. So the big question is, does it work? So in the December data, we're comparing a time stack from the drone and a time stack from the truck. And the cross-shore distance is down here on the x-axis. So 0 is on shore. It's right here, just north of this first pressure sensor. And then we're looking at time here going up on the y-axis. So this is the same thing as it would be if you were looking at an Argus time stack. We're just using LiDAR here. And you can see that with the drone, you do get great returns off of the beach and the water. This is a 900 nanometer wavelength drone. So it's meant to perform a little bit better with these wetter surfaces. And conversely, with the truck itself, with this 1550 nanometer wavelength, it does get pretty poor returns on the wet sand itself and shadowing with the large waves. So you can see the shadowing here in this box as we're comparing this yellow patch from the drone and this sort of blank nothing from the truck. And so this is pretty good to look at. The truck LiDAR, we use this for beach surveys again. So this is made to look at cliffs, not necessarily made to look at wave runup. And so when you get into the beach, you do have to do quite a bit of interpolation to understand where the foreshore is, whereas the drone can just sort of tell you that. And in February, it was a similar situation where you did get great returns from the drone itself, but you notice that there's these big white spots here, and that's because it was a great day. It was glassy, it was beautiful, and the LiDAR does not like glassy and beautiful. So we didn't have that many returns as you probably extending past about 60 meters past the back beach point. And so that is one caveat to the greatness that is the LiDAR drone. So one of the example uses that you could take from this is inverting for surf zone bathymetry. So this has been done with cameras and also with LiDARs in the past previously. The perks of having the LiDAR out there is that you already know what the mean sea surface is. You just take the mean of your time series that you have scanning on a line. So you don't have to mess with tide levels or anything like that in order to come up with what your depth actually is. And then the LiDAR itself, it's really high resolution. So we were scanning at 10 hertz and we gridded to 10 centimeters. So this gives you a great opportunity for tracking the celerity itself. So we're comparing December versus February here. This gray line here is the bathymetry that we collected with traditional stuff. So that's the jet ski and the push dolly. And then over here, this is the still water level range as measured by the LiDAR itself. So we're trying to find out what the depth is. And so what you can do is stack up all these waves together and just track the crests as you head into shore. So this is the cross shore here, and note that we're looking at things, I think I separated by 2 seconds here. And so you can just track the speed of the wave as it goes up towards the beach. And so this is something that's been done previously. I'm not trying to say that this is anything new here, but the novel thing is that you can do it from a hovering instrument, which is very exciting. And so if you track the celerity and follow it in, get your wave speed, you can invert for H here. And so we do that, but it does seem kind of big. But this is the surf zone. And so of course we have bores. So you can add a correction onto there where you would assume that the bore is going to be going a different speed using bore theory correction. And then you can try invert for H again, or little h. Now, if you're looking at wave height, you can extract this from the LiDAR. You don't have to make any sort of guess with any sort of model. You can just go ahead and look for the wave trough. And so the distance between the crest and the trough, we're calling our wave height here. And we're able to incorporate that into this model. And when you do, you can come up with a much better inversion using the LiDAR and all the information that the LiDAR does give you. And so I think that this method is really promising for us in terms of going to locations that we don't always necessarily are able to survey in situ. So at Imperial Beach, like I said, sometimes it is polluted. We don't want to be sending people out on a jet ski or into the water there when there are warning signs on the beach about contaminated water. And so this offers one solution for getting bathymetry sort of on the fly, literally. And so that idea with the new observational tools here is that we're trying to feed all this information back into the forecast itself. So how can we improve the forecast? What we're trying to do is take this information from the drone. We have the ability to rapidly deploy it. Again, we're going to remote locations. You can get your usual beach and wave and run-up scans. You can do your depth inversion, but you can also do a whole host of other things that you could do with a LiDAR, such as understanding the wave transformation at different points along the surf zone. You can tell from the last plots that we're looking at about 100 meters maybe in length. So that's great for better understanding the physics itself of what runup is doing. But there are, again, some lingering questions that we do have with how to improve the forecast here. And so I'm gonna sort of leave this talk with kind of a question, maybe for you all, if you are able to answer it. We did have a recent flood event in January of 21 that impacted several of our sites, but Cortez Avenue, the one that I showed on the first slide, was very over predicted. So we expected that there would be flooding all along at these points, but Cortez Avenue right here did okay. And so one of the questions is why? Did we not get the bathymetry right? Was there some sort of a bar offshore that we weren't able to get? This is something that we're trying to look into, but there is a further mystery, and that is cobbles. And I saw that Hero had logged into this, so maybe he can say something. But with the lingering questions that we do have, that is, these cobbles seem to be intermittent on these California beaches, and they show up, they disappear, and we don't always have the ability to survey them because we're not out there enough. They seem to go away, especially if we're doing something like a quarterly survey. And so one of the things that Hero with our group and Adam Young have been doing is they're mapping and understanding how cobble works in Southern California. So we have these mixed sand and cobble beaches. And what we want to know is how these do affect our coastal hazard forecasts. What are we not getting right when we do have these cobble information, or these cobble berms that are built up in the back of the beach? So it could have been an offshore bathymetry thing. It could have been the cobbles. It could have been a combination of both. We're still looking into why we got that wrong. But that's the best part of science, right? So I'll leave you with this. With the coastal hazard forecasting, we are incorporating ongoing LiDAR observations by our amazing field team, and using remotely sensed bathymetry. We're starting to get into that, baby steps here. And we're trying to understand the physics, again, basically going back into what the wave runup is doing, what the boundary conditions are, still kind of unknown, and the cobbles, and then understanding the approximations that we use in these formulas and continuing to test those. And the idea with getting these very thorough studies at one spot is that if we learn on this very, very local scale, we're hoping to apply it more in a regional sense. So that's the direction that we're going in the future. And with that, I will leave it up for questions. Hopefully I didn't run over time here.
Thanks a lot, Julia. Really great talk and some exciting research you're doing. I'm sure there's a number of questions, I imagine, for Julia. Does anybody want to just either type their question